Okay, we're back, week 6. Welcome back. I know there was no midterm on week 5. Usually there's a midterm on week 5, but because this class is now distance learning, I thought that doing a quiz every week is a little bit better than that. I want to talk about some things today. I want to talk about a couple of issues people are having with their triangles, with the power factor calculations, also with the sine waves and exactly what those mean. So I want to start out with a couple of kind of bigger, broader representations of what's going on. I want to look at two different circuits, and I'm not going to actually do the whole circuit. I'm instead just going to give you some numbers from those circuits, and we're going to go from there. This first circuit I'm going to say we've already solved, and let's say for the sake of arguments, he says he drops the eraser on the floor, these are inductive circuits. So they have, if they have capacitance, they have more inductance than capacitance. So when we do our final analysis of them, when we draw our sine wave, we're going to work from Eli. We're going to say that the voltage follows the current. This first sine wave, I'm going to say that power true equals 700 watts. And power reactive, we already calculated this, okay? We're just kind of skipping forward, equals 300 var. So if I've got a power true of 700 watts, and I've got a power reactive of 300 var, I need to do a little bit of calculation to figure out what my hypotenuse is, which is going to be in VA, and that's going to be my power apparent, right? Power apparent. That's the first one. We'll do a little bit of math here, right here in a second. The second circuit I want to do is essentially the same thing. And I've drawn it pretty close, but use your, actually let me redo it a little bit. Where's my other eraser? It didn't drop on the floor. Let's make this guy even smaller and shorter. I'm going to make this triangle, and I'm trying to draw them to scale. I'm going to say this is 100 var, and this is still 700 watts. And we'll figure out what the VA is on this, still a right triangle, and figure out what the change was on this. So let me clear this out and do a little bit of math here. So on this one up here, in order to find the VA, I'm going to take the square root of, I'm going to take the square of 300, add it to the square of 700, and then take the resultant square root. So it's the sum of the squares equals, the square root of the sum of the squares of the opposite and adjacent equals the square of the hypotenuse. I think I said that right. You guys ever watched Wizard of Oz? The Scarecrow says that, I think, when he finally gets his brain. So I'm still waiting on mine. 300 squared plus 700 squared equals 580,000. Second square root, second answer gives me 761.58. 761.58 VA. Down here, let's do the same thing. Let's go ahead and go 100 squared, whoops, wrong button, 100 squared plus 700 squared, and that equals like 490 gazillion. Oh, you know why? Because I didn't add the plus sign. 100, you gotta watch these calculators. I find a lot of the problems I see are because you did something wrong in the calculator. So let's get back to what I'm doing. 100 squared plus 700 squared equals, that's more like it, 500,000. Second square root, second answer equals 707.11. 707.11 VA. So notice a couple of things. This triangle has a larger reactive power compared to this triangle. This triangle's reactive power is a little less than half of the true power, whereas this one is only 1/7 of the true power. And as a result, the VA on this one is much closer. 707 is pretty stinking close to 700. 761, it's close, it's still a relatively similar number, but it's a good bit more than 700. It's not negligibly more than 700. And if we go ahead and solve the rest of what we do on these triangles, we'll see a couple of other correlations. So the next thing I like to do at this point is solve for power factor, right? And power factor is it's that unitless number that we can either express as a decimal or we can express it as a percentage. And all it tells me is how much of the power that I'm actually paying for, how much of the power that I get from multiplying the current in the wire times the voltage across the load am I actually using in heat dissipated or work done. So how much of this do I pay for, do I get? The video that I asked you to watch makes the analogy of a glass of beer. How much beer do I get compared to the head? In the analogy, the beer plus the head, the foam on the beer, equals power apparent. The foam is the reactive power, because it's there, but it really doesn't do us any good. And the beer is the true power, is the real power, is the actual liquid beer. So that's an interesting analogy. I'd never seen it before today, and I like it a lot. So I'm going to go ahead and get my power factor. Now remember, my power factor is watts over VA. It's not VARs over VA. It's not watts over VARs. I had people do both of those on the quiz, okay? It's watts over VA, or power true over power apparent. And in this case, it is going to be 700 divided by 761.58. I don't even know what that is, but I'll put it in my calculator and tell you. 700 divided by 761.58, that equals 0.91914. So I'm going to call that 0.9191, because the next digit's a 4, so I can round down, or 91.91% power factor. That means that 91% of the power that I'm paying for is power I'm actually using. I have a beer that's 91% beer and a little less than 10% head. So that's not bad. That's not terrible at all. What happens in this circuit, though, where somehow we've reduced the VARs to 100? Our watts stayed the same, but our VARs reduced to 100, and my VA, therefore, is closer to that. So my power factor here is going to be 700 divided by 707.11. So if I go 700 divided by 707.11, that's going to equal 0.9899. And the next digit's a 4, so I can't round up. I have to keep it at 0.9899 and round away the 4. 0.9899, or 98.99% power factor. That means that I've got a beer that a real professional bartender poured for me here. It's 98.99% beer to head. So that guy tilted the glass and the beer when he poured that thing, if you guys are beer connoisseurs. Those of you not 21 yet, don't listen to this part. So 98.99% is my power factor, which is pretty good. Angle theta. How do I determine angle theta? Well, it's invert cosine, which I think is cos -1, not -1 cos. I always get that wrong. In this case, 0.9191. In my calculator, clear, let's see, second cosine 0.9191. Did I do that right? Yep. Equals 23.21 degrees. Whoops. 23.21 degrees. Now I did round that up. My calculator told me 23.205, 5 rounds up. So I'm going to call that 23.21 degrees. I challenge anybody to show me 1/10 of a degree on the sine waves that we draw, right? So 23.21 degrees. Now that angle is this angle right here. This is angle theta. And I think you guys got that pretty well. It's the angle between the adjacent. Now this side is called the adjacent because it's next to that angle, right? This would be, with reference to this angle, this would be the opposite side. But it's the adjacent over the hypotenuse. The hypotenuse is always the hypotenuse regardless of what angle we're calling about. So this angle's angle is the cosine of adjacent over hypotenuse. And if you know your SOHCAHTOA, your trigonometry, you'll remember that from that. And that's how we got that. I'm not going to go into a big trigonometry lecture. I've been avoiding that all term. But we got that angle theta. That angle theta applies to that. It also applies, and I'm going to do that I'm going to erase these because we already know what they are. On my sine wave for this circuit up here, I'm going to draw a sine wave. Now I already told you it's Eli, right? So voltage is going to come before current. So once I've drawn my first sine wave, I'd like to go ahead and figure out where things are on that sine wave. Now any sine wave I draw that has to do with electrical circuits, we can call the whole wave, and that is from 0 to high, to cross 0 to low, back to 0 again equals 360 degrees. And that's with respect to the source that built it. There's a rotational source that is creating this sine wave, and since that rotational source is cutting across lines of flux, if you remember from earlier lectures, when it's parallel to the lines of flux, it's generating very little voltage or current. When it's crossing, when it's perpendicular to the lines of flux, it's generating the most in one direction or the other. That's why a rotational force gives us a sine wave when we're thinking about the magnitude, the amplitude of our current or our voltage. And that's a really handy thing because I know I can take a circle and I can cut a circle into 360 equal pieces and call those degrees. And if this represents this, I can cut this into 360 equal pieces. And if that's the case, with regard to this sine wave only, that's my 90 degrees. So if this is 0, this is 90. Where it crosses 0 again is 180 degrees. Where its low point again is 270. And back to 0 is 360. I saw sine waves that people went ahead and did this. You don't have to mark all these things on your sine wave on your quizzes, but people did and they got it completely wrong. They were at 270 here, or they basically showed me that they didn't understand the concept by what they put down. So I want to make sure you understand that. Now, that's with respect to this sine wave only, so I don't even need these things right now. I'm going to use, compared to this sine wave, I have to draw another sine wave that's my current sine wave, and that current sine wave has to be, where's my angle theta? Oh my God, I lost my angle. 23.21 degrees different than this end. And in fact, it's my current that I'm drawing, so it has to lag my voltage, right? So if this is my voltage, my current is the next one out. If this is 90, this is about 45, and 23 is somewhere in the neighborhood of halfway to 45. So my second sine wave should follow the first one at about what I'm calling 23 degrees, 0.21 degrees difference. Now, nobody has to be perfect when they draw these, but if you're going to mark things, your marking at least has to be correct. If I'd drawn this sine wave out here at 90 or past 90, it'd be wrong. If I put something other than 23.21 in here, it'd be wrong. If I didn't also go ahead and mark and say, that's my voltage, and that's my current in some way that I can understand, just show me you understand that voltage is before current, this would be wrong. But check it out, that's my sine wave for this one. Down here, my sine wave for this one, if I've got a power factor of 98.99, my angle theta, this angle here, has changed, hasn't it? Clear, clear, clear. And I'm going to go ahead and put in second cosine, which is invert cosine, of 0.9899, equals 8.15 degrees. So check it out. Angle theta here went from 23.21 degrees when I reduced my vars from 300 to 100 but kept my watts the same. My angle theta essentially went down a third, right? Because 3 times 8 is 24, close to 23.21. 100 out of 300, it's about a third. It went down about a third because of the relationships here. And also, this number got a whole lot closer to this number. The hypotenuse on this triangle with the smaller angle theta is very close to the size of the resistive power, the true power. Whereas here it's a little bit more than the true power. As this angle theta gets smaller, my hypotenuse gets closer to the size of this. And that's because I calculate this angle theta with power factor. And power factor is just the relationship between those two things. And that all happened because I changed the VARs. Let's go ahead and draw this sine wave. Keep that in mind. We changed the VARs, we changed angle theta, we reduced the VARs, angle theta went down, power factor went up closer to 1. If these two lines were the same size and there was no reactive power, I would have perfect power factor, or unity, power factor of 1. Something's happening in the building. There's a big rumble. Hope it's not burning down. So on this one, I've got my first sine wave. In this case, I'll say it's voltage, but I could draw another one out in front of it and call the one out in front of it voltage. Let's do that, just so you can see the same thing. So again, there's my 90 degrees on this. I've got 8.15, so I want about 1/10 of this, or even less than 1/10 of this. Now I'm going to draw my second sine wave on this one on the other side of it, but I'm going to try and use this as a marker to say, okay, this is 9 or 10 of what I need. So 1/9 or 1/10 of that's going to be pretty stinking close, but out here. And I'm going to follow behind it the whole way. Well, I didn't get very perfect in there. I missed it a little bit. But this here, I can say, is 8.15 degrees. Now, the crucial thing is it's Eli, right? So voltage has to be in front of current. Now, the first one I drew this time is the farther one. It's that way. So I'm going to label it as current. The second one I drew, the one I didn't draw as nicely and drew out this way from it, that one's going to be voltage, because voltage leads current in an inductive circuit. If it was a capacitive circuit, it'd be the opposite. And that's really crucial, and you're going to see why here in just a second. These are some things I see you guys doing wrong. I wanted to talk about these differences, and I wanted to talk about the fact that we can actually do what we've just demonstrated here. We can take a circuit and we can change what the reactive power is in that circuit by altering it, by adding either a capacitor or an inductor. Because, as you learned real briefly in the last video, the capacitive power and the inductive power are 180 degrees from each other, and so they cancel each other out. Just like in a parallel circuit, the current through the capacitor is opposite the current through the inductor. And the current of those two, for total current's sake, cancel each other out. You're going to find that out here in just a second when we do a series circuit, that they cancel each other out in series with respect to their own values. The capacitive reactance is 180 degrees out of phase with the inductive reactance, so they cancel each other. So by adding something to a circuit, we can actually reduce this number. As that number gets reduced, everything gets closer to where we want it. I'm going to stop this video right now, but there's another video I'm going to start in just a couple of seconds, and it will continue explaining this.